Hello, welcome to Unit 8, Lesson 2. This is Professor Blackman. In this lesson, we're going to be talking about graphing polynomial functions. If you haven't watched my Unit 8, Lesson 1, please go back and rewatch that because a lot of what we're going to be doing in this lesson is putting what we learned in Unit 8.1 into play. So a big thing of what we're going to do is we're going to graph polynomial functions. We'll do a few problems on the intermediate value theorem. Right here on this box right here, if you want to go ahead and pause this video and put this into your notes, I highly recommend it, especially numbers 1, 2, and 4, which is the ones I really focus on. All right, let's go ahead and get started. All right, so first we're going to look at in behavior. I can see that this is a negative. I can see that this is negative and an odd function because it's a negative 1 that is negative and 3 is an odd function. So a negative odd function has in behavior that is going to start here and end somewhere down here. All right, think of that as y equals negative x. All right, now our next thing we want to do is we want to focus on our x intercepts. So I'm going to go ahead and just draw an axis right here. And so let's look at our x-intercepts. So in order to find our x-intercepts, we need to factor this and get it factored. So I'm going to factor by using GCF. So I'm going to have f of x equals negative, leading terms negative, x squared. When you factor that out, you get x minus plus 2. Go ahead and check that. Negative x squared times x, negative x to the third, negative x squared times 2 is negative 2x squared. All right, so here we can see that we have x equals 0 and x plus 2 equals 0, which is x equals negative 2. This is x squared, so this is a multiplicity of 2. And this is a multiplicity of 1. All right, so I'm going to go ahead and put 0 as a x-intercept right there. And then I'm going to go out and put negative 2 as an x-intercept as well. The next step would be to figure out your y-intercept. Well, this one's very easy because, well, if you put x as 0, 0, 0, you get 0. So our y-intercept is also 0, 0 because we already have 0, 0. So it's only going to cross this y-axis in one spot. All right, so multiplicity of 2. Now we can go ahead and we can do a quick rough sketch of this. So I know I'm starting somewhere up here. This has a multiplicity of 1. I'm going to just put a times 1 for here. And this one has a multiplicity of 2. I'm going to put a times 2 there. So this is going to go down, cross through, bounce off that one, and end up somewhere down there. Now, this little valley could be deeper. It could be shallower. But this is the only place, these are the only two places it's going to cross the x-axis, and this is the only place it's going to cross the y-axis. This could be very shallow, or this valley could be really deep. But this will give you a rough sketch, and most of these problems, especially in my homework, are just matching because you're just doing them very quickly. All right, let's go ahead and look at our next one. All right, this x to the 5, this is, so we have a 1 out in front, so that's positive 1. And this x to the 5th means it's an odd function. So that means for in behavior, positive and odd means we're going to start somewhere down here, end somewhere up there. Okay, let's go ahead and do x-intercepts again. Start by factoring. GCF here is x to the third. So f of x will equal x to the third. When you factor out an x to the third, you get x squared minus 4. There's that difference of squares that pops up a lot. So then we have x to the third. Difference of squares becomes x minus 2, x plus 2. And so here we have x equals 0 with a multiplicity of 3. X minus 2 equals 0, which becomes x equals 2, which has a multiplicity of 1. And x plus 2 equals 0 gives you x, subtract 2 from both sides, negative 2. So let's go ahead and just summarize all of our x-intercepts we have so far. We have 0, 0 as an x-intercept. We have 2, 0 as an x-intercept. And we have negative 2, 0, all as x-intercepts. This 0, 0 occurred 3 times because of the x to the third. So this has a multiplicity of 3. And both 2 and negative 2 have multiplicities of 1. One thing to note, that because 0, 0 is an x-intercept, we also know that that will be our y-intercept as well. Because 0, 0 is x-intercept and y-intercept if it's 0, 0. So let's go ahead and put these on our graph now and do a rough sketch. So 0, 0 right there, negative 2, 0, and 2, 0. Now these all have odd multiplicity, so we all just go through. There is no bouncing off because there's no even multiplicities. So we start down here. And it goes somewhere here, through there, and up. Now again, this hill and this valley could be a lot higher or it could be a lot lower, but this is just a rough sketch to kind of just give you an idea of what it looks like. All right, let's look at our next example. All right, these two examples are in factored form, which makes finding the x-intercepts easier, but the y-intercepts require a little bit more work, and looking at in behavior kind of take a little bit more work. So what we're going to do is kind of do just like a quick multiplying out. So h of x equals, well, we need to see how many x's there are. X times x times x times x. So that's x to the fourth. Now, what I need to do is figure out if I put a 0 in here, what's going to be here? Well, if I put a 0 in here, and negative 4 and a 1 and negative 2, that all multiplies and gives me a 0. So this will be plus something, 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 plus a 0 at the end. So that just lets us know that the constant at the end will be 0. All right, so with x to the 4, there's a 1 that's positive, and this is an even function. That means when we do our quick sketch of a graph, we know that positive and even means here and ending up here somewhere. All right, now let's look at our x-intercepts. X-intercepts, first x is x equals 0, which will give us 0, 0. X minus 4 equals 0, which gives us x equals 4. So 4, 0. X plus 1 equals 0, which is x equals negative 1. So negative 1, 0. X minus 2 equals 0. Add 2 to both sides, and you get 2, 0. Now, none of these have a multiplicity other than 1 because there is no exponents anywhere. And again, 0, 0, that's also your y-intercept. So that's your y-intercept and x-intercept. 1, 2, 3, 4. 4, 0 is a point. 2, 0. And negative 1. So as a quick rough sketch, we go through, 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 and through. And we end up something like that. And again, these hills or valleys could be lower or higher, but this is just a quick rough sketch. All right, let's look at number 4 now. Okay, so first off, we need to multiply all this out and just kind of see quickly what it is. So negative x, xx, and xx. So 2, 4, 5. So we get negative x the fifth. And if I plug a 0 in, I get 0 times other things, but so it ends up just being a 0. So this ends up being a 0 at the end. All right. So that will let us know that our y-intercept is also 0. Okay. So this is a negative odd function. So that means negative odd, think of that like y equals negative x. So that would be here, and here is our end behavior. So now let's look at x-intercepts. Okay, for x-intercepts, we're going to use a 0 factor. So negative x equals 0 means x equals 0. So 0, 0. Okay. X minus 1 equals 0. So x equals positive 1. So 1, 0. And this has a multiplicity of 2 because of that exponent on it. Take x plus 4 equals to 0. Get x equals negative 4. And so negative 4, 0, which also has a multiplicity of 2. So go ahead and put 1, 2, 3, 4. Negative 4 is right there. We have a positive 1, which is right there. And 0, 0, which is our y-intercept, and x-intercept in the middle. So we are going to bounce off this one because remember this one has times 2 here, and this 1, 0 also has times 2 for multiplicity. So we're going to go down, bounce off, go through, bounce off, and come down. So that's kind of your rough sketch there. And again, this hill or valley could be a lot lower or higher. All right, let's look at another example. All right, so we're going to talk about the intermediate value theorem, which is a very mathy theorem, and I want to help kind of make sense by giving you a picture. So let's say you have a point here, A and B. Okay, so there's a point up here. So on the on the y-axis, this would be what the theorem would call P of A, and then let's say down here, this would be P of B. All right. So basically, this is your x-axis, and it's saying that if A and B have opposite signs, then when you plug them into the function, then there has to be a 0 because this point here has to come down here. Now, we know it, and it says it has at least 1. So at least 1, 0. Because it could do the direct route, or it could take a scenic route and, hit it multiple times. But either way, it's going to cross and have a 0 somewhere between the two. All right. And so if, it was down here, and up here, again, opposite signs, the only way to get to them is to connect like that. Now, the second part of the intermediate values theorem says we cannot use it if A and B have the same sign. So let me go ahead and do a quick rough sketch of that. So let's say A and B are both positive. So A and B are both positive here. Now, the reason we say we cannot use the intermediate value theorem is because, again, we could take the direct route there, and guess what? There's not a zero. But we can also take a scenic tour and have a zero. So basically with the intermediate value theorem, if you have opposite signs, like the first examples, you say, yeah, there's at least one zero. There could be more than one, but you can say there's at least one. If at any time you get A and B giving you both positive or both negative, then just say you can't use the theorem because of this example here. Because we could go straight through, not have a zero, take the scenic tour, and have a zero. So opposite signs, there's at least one zero. Same signs, whether it be both positive, both negative, then we just say cannot use the intermediate value theorem. All right, so let's look at examples for the intermediate value theorem. All right, so let's start with this function that's here, and we're going to plug in f of a, which in this case is f of -5. When we plug that in, we get -5 to the third power, which is -125, plus 3 times -5 squared, which would be 25 times 3, which is 75, minus 9 times -5, which would be plus 45, minus 13, minus 13. And let's simplify that. And we get -18. So now let's look at f of b. And so f of b, which is f of -4, which would be -4 to the third power. All right, so now let's look at f of b. So f of b, which is f of -4, which when we plug in is -4 to the third power plus 3 times -4 squared minus 9 times -4 minus 13, which when we simplify that, all we get 7. So as you see, we have -18 and 7. These are opposite signs. So then we can state by intermediate value theorem, there is at least 1 0 between -5 and -4. All right, let's look at our next example. So we're going to start with f of a, which is f of -3, which gives you 3 times -3 squared minus 2 times -3 minus 11. So that's 9, 3, 27 plus 6 minus 11, which simplifies to 22. All right, let's look at f of b, which is -2 in this case. So 3 times -2 squared minus 2 times -2 minus 11. So simplified, 3 times 4, 12 plus 4 minus 11 gives you 5. And as you see here, these are the same sign, while these here were opposite signs. So all you can say in problem 2 is we cannot use the intermediate value theorem. Because again, if they're the same sign, we cannot use the intermediate value theorem because we could go directly from 22 to 5 or we could take the scenic door. All right, that's all I have for you today. Happy studying.